Welcome back to Honors Calculus. In this video, we'll finish up our discussion on differentiation rules by revisiting the power rule. Remember the power rule we proved for natural numbers. The derivative of x to the n is n times x to the n minus 1. We used previously the assumption that this rule would continue to work for more generalized numbers. Specifically, we tried to use it for 0 and -1, which are not positive integers. In this video, we're going to look at showing that it works in general. Well, not quite in general. We are not going to develop enough tools this semester to show that the power rule works for all real numbers, although it will turn out that it does. We do already have the tools necessary to show that for all rational numbers, the derivative of x to the n is n times x to the n minus 1 power. But for the sake of time, instead of proving that, I just want to dive in and start using it. To take the derivative of square roots. Right? We've seen polynomials, we've seen rationals. Now with the generalized power rule, we can take derivatives of radicals. And we've also seen trigonometry. So all of the kinds of functions that you're familiar with, we will be able to differentiate at this point. The derivative of the square root of x remember, the square root is the same thing as the 1/2 power. And by using the power rule, this is going to be 1/2 times x to the 1/2 minus 1. 1/2 minus 1 is -1/2. Negative powers push things from the numerator to denominator. So this is 1/2x to the 1/2 power. And x to the 1/2 power is still a square root. So this is 1/2 square root of x. And of course, we can also combine this generalized power rule with the chain rule. Say we need to take the derivative of the cube root of the sine of x. Well, using the generalized power rule, this is going to be the same thing as sine of x to the 1/3 power, which is 1/3 times sine of x to the 1/3 minus 1 times the derivative of sine of x (1/3 minus 1 is -2/3). The derivative of sine is cosine. So we end up here with cosine of x over 3 times the sine of x to the 2/3 power, which, depending on the application, might be better to leave at that. Or I guess we could simplify and call this the cosine of x over 3 times the cube root of sine squared of x. I'm not sure between those two which one is the better version. It depends on what you're trying to do with it. And this can really start to get to be a mess if we try to combine things with some more powers. Right? Sine and cosine have relatively straightforward derivatives. But if I have a square root of, say, some mess involved, 3x squared minus 7, well, now it really gets to have some fun. All right, this is the derivative of 3x squared minus 7 to the 1/2 power, which is, by the power rule, 1/2 times 3x squared minus 7 to the negative 1/2 power times the derivative of 3x squared minus 7. Right, 3x squared minus 7 to the negative 1/2 is 1 over the square root of 3x squared minus 7. And the derivative of 3x squared minus 7 is 6x. That 6 will cancel out with the 2, reducing down, so we end up with 3x over the square root of 3x squared minus 7. All right, and one more just for fun. We can mix this in with the quotient rule. The derivative of the square root of x over x plus 1. This is going to be a nightmare. It's not going to be that bad. It's just going to be a lot of be very careful and make sure that you don't put anything in a wrong place. All right, so my f is the square root of x, g is x plus 1, f prime is 1 over 2 square root of x. We already took the derivative of square root. I'm not going to go through it again. G prime is 1, at least that's one thing going for us. So using the quotient rule, we are going to end up with f prime g minus f g prime all over g squared. F prime is 1 over 2 square root of x. G is x plus 1. F is square root of x. G is 1. And then we have x plus 1 squared in the denominator. We end up with a compound fraction, a fraction that has fractions in it. So get rid of that by multiplying numerator and denominator of the big fraction by 2 root x. All right, x plus 1 over 2 root x times 2 root x is x plus 1. Root x times 2 root x is 2x. Well, 2 times the absolute value of x, but because we have x in a square root, I know that x has to be positive for this thing to be defined. I don't have to worry about absolute value. And then we'll have 2 root x times x plus 1 squared in our denominator. Combine some like terms, we get 1 minus x over 2 root x, x plus 1 squared. As far as I'm concerned, that's a great place to end things. But technically speaking, we're not done, because square roots and denominators of fractions are considered bad things. So let's rationalize by multiplying top and bottom by root x, and we'll end up with 1 minus x times root x all over 2 root x times root x is x, and then we have x plus 1 squared. I do prefer keeping things in factored form instead of multiplying things out. So this is definitely where I'm going to leave it. I am not going to try multiplying it out. It is not better to have this written as root x minus x root x all over 2x cubed plus 4x squared plus 2x. That is not a help in any way, shape, or form. Let's leave it like this. All right, let's try writing that again in a way that's actually legible. I would like you to try this one, which is not as bad as it might look at first glance. The derivative of 1 over the cube root of x squared minus 5. Take a few minutes, see what you can get out of this one, and I'll see you next time.